Welcome to this video on graphing rational functions. So, what is a rational function? A rational function is a polynomial divided by another polynomial. And what we'll see in this video is that graphs of rational functions can be complicated, but can actually be simple to do without a calculator as long as you can find certain key features of the rational function. For example, if you can find the vertical asymptote, which is a vertical line that the graph merges with and never reaches. If you can find the end behavior, which is going to be either a diagonal or horizontal asymptote in most cases, again, a line that the graph merges with and typically doesn't reach. If we combine the so-called holes in the graph, and if we can find the y-intercept and the x-intercept, then we'll be able to show that graphing rational functions can be relatively straightforward, even without a calculator. Again, the key features that we'll show in this video are how to find the vertical asymptotes, how to find the end behavior, which can be a horizontal or a diagonal asymptote in most cases, how to find holes in the graph when they exist, and how to find intercepts. And if we can do this, it'll turn out that graphing a rational function is not that complicated after all. So let's look at our first key feature of 4, the vertical asymptotes. Here's an example. I'm going to go through how to find a vertical asymptote, but then I'm going to explain in detail why the procedure I followed is meaningful and actually usable in this context. But first, let's look at a graph and let's start with the how. How do you, as a student, go about mechanically finding a vertical asymptote? Well, here's the rule. I'll pause while you read it. So we need to find a value of x for which the denominator is 0 and the numerator isn't. And if we can find that value, or those values in some case when there's more of them, then we will have found the values of the vertical asymptotes. Well, typically we set our denominator equal to 0 to find these. And if you set your denominator equal to 0, you'll find out that x is 4. But go ahead and read the 2 bullets again and convince yourself that 4 meets both of the bullet conditions. So, it does, in fact. If 4 makes the denominator 0, and it doesn't make the numerator 0. And therefore, we're going to have a vertical asymptote at x equals 4. And as far as the mechanics, the step-by-step process you go through to find a vertical asymptote, it's pretty straightforward. Set your denominator equal to 0, and make sure that those values that you find there don't also make the numerator 0, which they typically won't, and you've got yourself a vertical asymptote, and that's the step-by-step of it. But it's more interesting to really ask the question, why? Why does that work? What is the meaning of all that? To understand why there's a vertical asymptote at 4, and it's not just because it makes the denominator 0. I mean, yes, that's true, that's the procedure, but why is it that 0 denominators cause vertical asymptotes? To understand that, try to follow me on this thought process. What would happen if we tried to plug 4 into this function? We would get something that doesn't exist. You may recall that division by 0 is not allowed in mathematics. 5 divided by 0 isn't 0. 5 divided by 0 doesn't have a numerical value. It's not a number. It's not a division problem you can perform. And so it makes sense that there would be no graph, no points on the graph that have an x-coordinate of 4. If we can't plug 4 into this function, then maybe we could plug a number really close to 4. So what would happen if we plugged 4.1 in for x? Well, it turns out we would get a very small denominator because 4.1 is so close to 4. And what happens to fractions when you have a very small denominator? Well, they get pretty big. I mean, think about it. How many times does 0.1 go into 5.1? Well, it turns out it goes in 51 times. This is a relatively large result. So what just happened is I plugged in 4.1 for x, and I got a result of 51. Doesn't that mean that this graph passes through the point 4.1, 51? So where would that be on the graph? Well, I imagine it would be somewhere around here. Notice I've gone, that point has an x-coordinate of about 4.1, and the y-coordinate, I'm not going to suggest that I measured it in any way or that 51 is exactly there, but it's worth pointing out that I just went as high up on the graph as I could without leaving the graph. So somewhere way up there is the point 4.1, 51. So what happens if I plug in another point close to 4? Let's go on the other side of 4 this time. Let's go slightly to the left of 4 by plugging in 3.9. If I plug 3.9 into this function, I once again get a denominator that's very close to 0. And when denominators are close to 0, the result of a division problem is relatively large, or in this case, large negative. So what just happened is I plugged in 3.9, and I got a big negative number for my answer, negative 49. Doesn't that mean that this graph must pass through or contain 3.9 comma negative 49? Oh, where would that be? Well, it'd be somewhere around here, I suppose. Notice that point has an x-coordinate of about 3.9, and I just went way down to the bottom of the graph to represent my negative 49. I have no intention of trying to scale or measure on the y-axis, which, by the way, we typically don't for rational functions anyways. You'll notice there's no markings on the y-axis. So the graph has to pass through those 2 points. So what just happened? I couldn't plug in 4 because it led to a non-calculable quantity. But I can plug in numbers slightly to the right of 4 or slightly to the left of 4. Now these 2 points, these 2 red dots that you see that the graph contains, I think we could convince ourselves that if we picked anything slightly to the right of 4, we would get a big positive answer, or anything just barely to the left of 4 would give us a big negative answer. So just by plugging in those 2 values, I'm convinced, and I hope you are too, that the graph is going to be approaching that vertical asymptote on either side as shown here. We'll look more at vertical asymptotes later, but that's the y in terms of why vertical asymptotes exist in a rational function. Now let's take a look at the second of 4 features called the end behavior. First of all, end behavior refers to what's happening on the far left and the far right side of a graph. And in the case of graphing rational functions, the topic of this video, we generally have the rational function approaching a line on the far ends, which may be diagonal or horizontal, depending on the circumstances. So let's take this example here and take a look at what the end behavior might be. Again, I'm going to cover the how and the why of this particular feature. I'm going to show you how to find end behavior, and then I'm going to talk about why those rules are the way they are. So how do you find end behavior? Well, here's the set of rules that govern what you would actually do as a student. I'll pause while you read those. This set of rules will become a little bit more clear once you start practicing the problems yourself, but to get a sense of how you go about doing this, the first thing we have to ask is if the denominator has a higher degree or not, because that will dictate which of these two rules we follow. If you look at the original problem, the numerator is a third degree polynomial. You could see that by imagining if you multiplied it out, you would get an x cubed. And the denominator is a second degree polynomial, so we're falling into the otherwise category here. Because the denominator does not have a higher degree, I'm going to have to use a process called long division and find the so-called quotient. And that quotient will more or less be my n behavior. Now, in order to perform the long division here, I have to actually multiply out the numerator. You may recall that long division is not performable unless the polynomials are all in standard form. I'm not going to talk you through the long division here. The purpose of this video is not to reteach long division, but it is a process that leads to a solution. And you can pause the video now and see if your memory is refreshed, or you could always go watch my polynomial division video in my YouTube channel. But the purpose here is not to review long division. That's something that you can do and should do if you need to. The real issue here is, what is the end behavior of this function? First, let me remind you that these two functions are the same. So to graph the one on the left, which is what I would be doing ostensibly, is the same as to graph the one on the right. And furthermore, the so-called quotient is this portion of the long division process. And it turns out that that quotient is the line that guides the end behavior. You'll notice that I've graphed the line y equals x minus 2 here, and if you look at what's shown in red, you can see that the graph of this function is actually approaching that line on the far right and also approaching that line on the far left. Now there's more parts of this graph in the middle that I didn't show. This is not the entire graph, but I've shown the end behavior of the graph and how it was dictated by the long division and the quotient of the long division that we did. Now, in terms of how do you find the end behavior, the rules on this page are the rules, and that's what you follow as a student. End of story. But that's boring if we stop there. We should probably delve into why it is that those rules are the way that they are. That's worth knowing as well, so let's talk about that. Why is that the rule? Well, to understand why, let's examine this so-called remainder factor over here, remainder term technically. And this remainder term is something we ignored when determining the end behavior. It didn't play a role. The end behavior was y equals x minus 2. That was our diagonal asymptote here. But the remainder does play a role in explaining why we ignored it, strange as that seems. Follow me on this thought process. It turns out that this remainder term approaches 0 when x gets really, really big or really, really big negative, or in other words, as x approaches infinity or negative infinity, that remainder term gets closer and closer to 0. And to give you a couple of examples of what I'm talking about here, let's pick a really big number for x. You'll notice I've taken the number 100 and plugged it into the remainder term. And when we work this out, the remainder term has a number that's pretty close to 0. Well, why is this close to 0? Well, because it's a fraction with a much bigger denominator. Well, okay, what made the denominator bigger? Well, the fact that the denominator, look at the remainder callout square in purple there, the remainder term has a higher degree in the denominator than it does in the numerator. So when I plug in large numbers, such as 100 for x, that remainder term is going to have a much bigger denominator because the degree is higher. And therefore, if the denominator is much bigger, the net result of it will be something close to 0. It's not exactly 0, but it's pretty close. Let's now imagine x got even bigger by plugging in 1,000 for x into the remainder term. When you plug 1,000 into x in the remainder term, you get a much bigger denominator than your numerator. Your numerator is big, but your denominator is way bigger. And when you do a ratio of numbers with a much bigger denominator, you get a number very close to 0, as we know. Now, I'm not suggesting that you should ever plug in 100 or 1,000 into the remainder term. In fact, you will largely ignore the remainder term for the most part. But when it comes to understanding why the remainder term is ignorable in terms of end behavior, the fact that it approaches 0 as x gets really, really big is pretty helpful to know here. Because if that remainder term is getting smaller and smaller and smaller, then it has less of an impact on the graph as x gets larger and larger and larger. And accordingly, therefore, we can essentially ignore it and say that the rational function will approach the graph of y equals x minus 2. It will approach the quotient because as x gets very large, the remainder term becomes virtually insignificant. And that's the why on the end behavior process. Let's now take a look at our third of 4 features of rational functions. These are called holes in the graph, and they're rare, but let's take a look at both how to find them when they exist and why that process works. Let's start with the how. Here's an example. How do we go about finding if there is a hole in this function, and if so, what it is? Here are the rules. I'll pause while you read them. Why these are the rules, we will get to in a moment, but first, how do we go about finding holes in this function? Well, I need to find a number that makes the numerator and the denominator both 0. If such a number exists, it's likely to be a hole in the graph. There's a very rare exception to that you'll never encounter. So this rule is pretty good for the purposes of what we need it for. One thing that you might benefit from doing is factoring the numerator and denominator whenever possible. Because by factoring the numerator and the denominator, you can see that x equals 3 would be a number that, on the one hand, makes the numerator 0, and on the other hand, also makes the denominator 0. In fact, you can tell by the factors that that's the only number for which this is the case. So by factoring, I have found that there's this number, 3 in this case, that makes both the top and bottom of this fraction 0. And I now have to plug that into the so-called reduced function. We'll be talking a lot about the reduced function here. So the reduced function is what you get when you cancel these two factors. For almost every value of x minus 3 divided by x minus 3 is 1. And therefore, you can cancel those out and get the so-called reduced function here. So now that I've canceled my like factors, I can now plug 3 into that expression, according to the rules of how to find a hole in a graph. Plugging 3 into that expression gives me an answer. And the 3 I plugged in, combined with the answer I got, makes the ordered pair that is going to be the hole in this graph. Now, what do I mean by a hole in the graph? Well, it turns out if we graph the entire function, there would be this one removed point that was not part of the graph. And how do we get this entire graph is something that we're going to get into in this video soon. But the point I want to make now is that we have this graph with a point removed from it. And that's what we mean when we say there's a hole in a graph. Now, from the pure mechanics of it, the how-to kind of a process, that's what you do. Follow these steps. If you can find a number that makes the numerator and the denominator 0, plug that into the reduced function, put those together, and you've got a hole in the graph. Great. As far as how goes, that's it. But what's more interesting than how, of course, is why is this a procedure that we're going to use? What's the meaning behind it all? To understand what the meaning behind the procedure is, which frankly you don't necessarily have to know depending on your teacher or professor, but I always recommend knowing why it is that we do what we do. Otherwise, we're just performing procedures, and that's boring. So why is it that having these canceled factors or number that makes the numerator and the denominator both 0, why is that create a hole in the graph in the first place is the real question. In order to answer that question, we need to look at the original function, which I have in factored form, but these two are the same, and the reduced function on the right. I'm going to say the phrase reduced function a lot of times here, so I'm referring to the x plus 5 over x plus 2 on the right side of your screen. Okay, follow me on this mental journey. The first question is, are these two functions the same? In other words, if I want to graph the original function, why don't I just graph the reduced version of that function? Well, there's some logic to that. Follow me on this thought process. Are these functions really the same? Well, to answer that, let's plug in x equals 3 to both functions. Something interesting happens when you plug in 3 to both functions. You get a different answer. For the reduced function, you get 8/5. But for the original function, and that's the one I'm actually trying to graph, you get 0 divided by 0. By the way, 0 divided by 0 is not 0. It doesn't exist. And so we have a function, our original function doesn't exist when x is 3, but the reduced function does exist when x is 3. So just from that one example, we can see that the reduced function and the original function are not the same function. It turns out, though, keep following me on this thought process, if x is any number except 3, the reduced function will have the same value as the original function. Right now, just think of any number that isn't 3. I don't care. Think of it. All right, I thought of 11. I don't know what you thought of. But any number that isn't 3, whether it be 11 or the number you thought of or some other number, when plugged into both the original function and the reduced function, they're going to give us the same value. And you can see why that's the case when you start to simplify here. Because looking at the 8s in the fraction there, those are going to cancel each other out. 8 divided by 8 is 1. And 1 times 16/3 is 16/3. And so, granted, I picked a kind of random number here of 11, and you probably are wondering, why did he pick that? Well, I just wanted to pick any number that isn't 3. And I think that this sufficiently makes the point that if x isn't 3, then the original function and the reduced function are going to have the same value. So what does that mean graphically? Remember, I'm trying to ultimately graph the original function. But what if I were to take the reduced function and graph that? This should pretty much look, and how I got that, by the way, is a subject later in this video, but here's the idea about the hole in the graph. The reduced function has all these points on it here, shown in red. But didn't we just say that as long as x isn't 3, the reduced function and the original function are the same? And therefore, when it comes to graphing the original function, I should have almost all of the same points I got from the reduced function, except when x is 3. Because when x is 3, the reduced function exists. The original function does not. So what do? Well, look at the graph. If we just remove the point from the original function, whose x-coordinate is 3, then we now have the graph of the original function. And that's the why behind finding the value of a hole in a graph. And now let's go to our fourth and final key feature of rational function graphing, the intercepts. Here's an example. So let's do the how before we talk about why. How do we actually go about finding intercepts? Well, there's two kinds of intercepts. To find y-intercepts, we set x equal to 0. And to find x-intercepts of a rational function anyways, we set the numerator equal to 0. Okay, let's look at the y-intercept first. Taking the original function, plugging in 0, and working out the math will tell you where this graph crosses the y-axis. Therefore, the y-intercept is 15/2. How do we find x-intercepts? Well, according to the rules of how, we set the numerator of the original function equal to 0. And when you set that equal to 0 and solve, it turns out that this function has two x-intercepts, 5 and -3. Now, as far as the how goes, that's it. Those are the rules. But again, those rules aren't that interesting unless you know why they're rules. So let's transition into that question. Why are these the rules? Let's start with, why is it that we set x equal to 0 in order to find a y-intercept? That seems a little backwards, doesn't it? It always did to me anyways. Here's the reason for that rule. Let's examine it graphically. We want to know where this graph crosses the y-axis. Well, what do we know about the y-axis? It contains points like 0, 3, 0, -2, 0, 5, or 0, 1. In fact, wouldn't you agree that any point on the y-axis is 0, something? In other words, every point on the y-axis has an x-coordinate of 0. And therefore, it's logical, if we want to find a y-intercept of any function, that we're going to set x equal to 0. By the way, that's not only a rule for rational functions, which is the topic of this video, but that's always how you find a y-intercept, regardless of what function type you have. Let's examine the other rule. Why do we set the numerator equal to 0 when we're finding x-intercepts? Why are we ignoring the denominator? Here's the reason. In general, generalizing beyond rational functions, the way we find x-intercepts is to set y equal to 0. Why is that a rule? Well, let's think about an x-intercept. It's a point on the x-axis. What do we know about points on the x-axis? Well, here's some examples. 4, 0, 2, 0, -3, 0, and -1, 0. Wouldn't you agree that all points on the x-axis are something, 0? In other words, every point on the x-axis has a y-coordinate of 0. So it makes sense that if we want an x-intercept of any function, that we should set y equal to 0. And again, that's generally true. That goes beyond just rational functions. Well, in this particular case of a rational function, setting y equals to 0 means that I'll be solving an equation fraction equals 0. Well, let's think about that. How is a fraction equal to 0? True mathematical fact. The only way that a fraction can ever equal 0 is if the numerator is 0. And that logic is why we ignore the denominator in this problem. And from that point on, we can continue to solve as we did in the how portion of the X-intercept. And that's the why for the X-intercept and Y-intercept rules. Now that completes the 4 basic features of a rational function. And now that we've gone through all 4 of them, we're now going to transition into some examples where we do them in their entirety. If you're still unclear about the 4 features of a rational function and how to find them, you may want to go back and rewind and watch those portions again. Otherwise, let's move on to our first full example. Let's take a look at this example. We're going to go through the 4 key features of a rational function. See what we can discover. First, I'm going to set up my graph. Notice that the x-axis is scaled. Traditionally, the y-axis is not. We're going to start with vertical asymptotes. Vertical asymptotes occur whenever your denominator is 0 and your numerator isn't. You can see from the algebra here that there are 2 places where the denominator is 0. And furthermore, at these 2 values, the numerator isn't 0 for either of them. Therefore, both of these are vertical asymptotes to the problem. Next, let's take a look at the end behavior. The rules for end behavior state that if the denominator has a higher degree than the numerator, which is the case here, that the graph will approach y equals 0 or the x-axis on the far extreme ends. I'll represent that by this dotted line. The x-axis will therefore be our horizontal asymptote. Now let's look for holes in the graph. Holes in the graph occur whenever there's a number that makes the denominator and the numerator both 0. No such number exists, therefore there are no holes in this graph. We know that no such number exists, by the way, because we know what makes the numerator 0, clearly -3, and we had already found what makes the denominator 0. -3 wasn't among those 2 values. So in conclusion, there's no holes in this graph. Let's now take a look at intercepts, starting with the x-intercept. X-intercepts are found by setting our numerator to 0. Therefore, we have one x-intercept, and here it is. Now the y-intercept can be found by plugging in 0 for x, which gives me this value, and I now have my y-intercept. Notice that -3/2 is -1.5, and that I wasn't particularly circumspect about where on the y-axis I put that. I'm not worrying too much about the scaling there. Now, I always like to ask myself, how does the graph approach the asymptotes? Because just knowing the 2 points that I know now doesn't really give me the full picture. Now, I could always, in the alternative concept, I could always just plot random points. By the way, you're always free to do that. No rule that says you can't plug in a random x and find out what y is. But to be a little bit more sophisticated, let's analyze how the graph approaches its asymptote, starting with a vertical asymptote, x equals 1. Now I can't plug in 1 to this function because the denominator would be 0 and it would therefore be undefined. But I can do something almost as good as plugging in 1. I can plug in numbers near 1. Let's start by choosing a number slightly to the right of 1, say 1.1. Now to do this, I'm going to recommend the factored form of the function. It doesn't matter, but it makes the arithmetic easier. So if I plug 1.1 into this function, and I work out the arithmetic, I get down to a point where I could probably use a calculator, but since the whole point is not to use a calculator, then there seems no point in reaching for that. I can tell that this fraction would work out to about 12-ish. You may not have the same decimal fraction skills, but notice how small the denominator is compared to the numerator. We know that this is going to work out to be a big positive number. So whether you can see that it's 12 or 13 or 14 or not, we know that there's going to be some point on the graph slightly to the right of 1 with a big positive y value. Whether you know it's 12 or not, I don't know that for sure either. I'm just estimating. Well, what does that point up on the graph tell me? It's not that it's plotted precisely, it certainly isn't, but it tells me that the graph has to be approaching the asymptote in that fashion. So now that I know what's happening to the right of x equals 1, let's find out what's happening just to the left of x equals 1. I'm going to plug in 0.9, which is slightly to the left of 1. And again, if you do the arithmetic, you may be able to estimate that this is also about 12-ish, but this time it's negative. And if you can't estimate decimals like that in your head, and maybe I'm off by a little bit too, it doesn't really matter. What matters here is that the denominator is so close to 0 that you're going to get a pretty big answer, or in this case, a big negative answer. So what does this tell me? It tells me when x is 0.9, y is a big negative number. I can plot that concept right here. And that, by the way, is not a precisely plotted point by any means. But what it tells me, the fact that I got a big negative number when I plug in 0.9 for x, tells me that my graph is going to be approaching the asymptote in a downward fashion on that side of the asymptote. So if you got a little lost in all that decimal work, I'm essentially plugging in a number just to the right of the asymptote and just to the left of the asymptote to get a sense of where the function might be going. Oh, one way that you can avoid all this arithmetic, remember we saw this problem just a moment ago, is to not do it in the traditional sense. What I like to do sometimes, especially when I'm in factored form, is I like to just write the words positive or negative next to each quantity. Now, this being in factored form is very important because all these positive and negative numbers are going to be multiplied by each other or divided. And because this is purely a multiplication and division problem, I know what a positive divided by a positive divided by a negative is. It's going to be a negative no matter what the numbers are. And this is a nice shortcut to not actually have to do the arithmetic, because if you can see that the answer is going to be negative and you don't know negative what, it still means that the asymptote, the graph is going to be going in a downward fashion near the asymptote on that side. So if you plug in 0.9, which is to the left of 1, and you get a negative answer and you don't know what the number is, does it really matter? It still gives you the direction of the graph, slightly to the left of that asymptote. Now, I just went through an extensive analysis of the vertical asymptote x equals 1. I will not go through that same analysis again for your sake more than mine. But applying that same analysis to the other vertical asymptote will give you that directional behavior of the graph. And again, without showing the work, I would plug in something slightly to the left of -2 and slightly to the right of -2 and get a sense of where my graph is going. The last asymptote to analyze is the horizontal asymptote, y equals 0. If you want to know what direction the graph is going, there are many ways to figure that out, but how is it approaching this horizontal asymptote? One way to do it is to plug in a really big number like 100. And you might think, well, I don't want to do all this arithmetic. Fair enough. Regardless of whether you do the arithmetic or not, you're going to get a positive divided by a positive times a positive. Now, you can tell that the numerator is going to be much smaller and the denominator is going to be much bigger, which gives a rationale as to why this function is going to have a value close to 0. But nonetheless, a positive divided by a positive divided by a positive is, of course, a positive. What does that mean? That means when I plug in 100, I get some positive number for for y, or for the output. Now, it turns out it's going to be a very small positive number, which we should expect. After all, our graph is approaching 0 as x approaches infinity. What does all of this tell me? It tells me that the graph is going to be approaching the x-axis from above, or the positive half, as we go further and further to the right. A similar analysis on the left side of the graph will tell me where the left end behavior is approaching, or how, I should say. So I could plug in any negative number, really, but why not negative 100? It gives the sense of it being far, far out there, and still makes it so that we can conceptualize the calculation. Now, you could do all the nasty arithmetic on this, or you could simply observe the numerator is negative, and the denominator is a negative times a negative, which is a positive. All told, this thing should work out to a negative. And what that tells me is that when x is negative 100, y is some negative number. It's going to have to be a very close to 0 negative number, because we know that the graph is approaching 0 as x approaches negative infinity. But in short, the fact that I know I'm going to get a negative answer there means that I'll be approaching my graph as shown there on the far left. And now that I've now that I've done the 4 basic features of a rational function, in addition to analyzing the behavior near the asymptotes, I have enough information to connect up all the pieces of this graph and get a rough sketch of what the original function might look like. Doing so will give me this. And that more or less completes the problem. The one change I would make is notice the horizontal asymptote y equals 0 hovering just on top of the x-axis. When I have either the x or the y-axis as one of my asymptotes, I tend not to put a dotted line over a solid one. I think it's fair to assume that the reader would suspect that the graph appearing to approach an axis is an indication by the author, us, that it actually is doing so. Let's take a look at this example. Let's go through the 4 main features of rational functions to try to build this graph. As usual, it's worth noting that the x-axis is traditionally marked with the tick marks, whereas the y-axis scaling, we want to be a little bit more free to not worry about it, so we will leave the y-axis scaling off. Let's start with vertical asymptotes. Vertical asymptotes occur for any value of x for which the denominator is 0 and the numerator isn't. So let's start by finding where our denominator could equal 0. If you do some basic algebra, you'll find 2 numbers that make the denominator 0. Pause if you need to see details. Now, remember, a vertical asymptote occurs generally at a number that makes the denominator 0, but not the numerator. Positive 3, however, is not going to be a vertical asymptote here, because it makes the denominator 0 and it makes the numerator 0. More on that later. Sounds like we have a hole in the making. But in the meanwhile, 3 does not qualify as a vertical asymptote, only negative 2 does. So there is our vertical asymptote. Let's now go to our second feature, end behavior. End behavior requires us to do long division unless the denominator has a higher degree. But the denominator doesn't have a higher degree. The numerator is cubic and the denominator is quadratic or squared, and therefore we have to do the long division to determine the end behavior. Here's the result of the long division. The work is not shown here, but the important part is that the quotient, in other words, ignoring the remainder, gives us the end behavior to this graph. What does that mean? That means that the line y equals x minus 2 will be a diagonal asymptote on the far left and far right ends of this function. Side note, a diagonal asymptote is sometimes called an oblique asymptote. Okay, continuing through the features of a rational function, let's look for holes in the graph, and I already sort of hinted that there may be one. A hole in a graph occurs for any x value for which the numerator and the denominator are both 0. There are very rare exceptions. You'll probably never see one. So, taking that into account, we may want to factor the denominator, which I've done here, in order to determine what number might make both the numerator and the denominator 0. And it's clear from the factorization here that positive 3 makes both the numerator and the denominator 0. Therefore, we're going to have a hole at x equals 3 in our graph. Whenever I discover there will be a hole in a graph, I like to reduce the function and use that from now on. So canceling out the x minus 3's leads us to this as our reduced function. And furthermore, plugging 3 into our reduced function and working that out will give us the coordinate of the hole in the graph. Now you can see that this hole is directly above x equals 3. It also has a y coordinate of 14/5, which is about 2.8. Well, it is 2.8. And I'm not being super worrisome about my y-axis scaling, and so I'll just put that anywhere. But the important, in the vertical sense, but the important thing is that I put that hole directly above 3 on the x-axis. Okay. I'll save my reduced function because with the exception of x equals 3, these two functions are equal. So any question I might have about the original function can be answered by the reduced function, unless x is 3. Let's move on to intercepts, starting with the x-intercepts. X-intercepts are found by setting our numerator equal to 0, and I'll use the reduced function to do that. If I use the original function, I would falsely find that x equals 3 is also an x-intercept, but that is not the case. And so this equation here, we'll notice, has no solution. You don't need formal algebra to see this. The only way x squared plus 5 could equal 0 is if x squared were negative 5. But a real number squared can't be negative 5. And since real numbers are all we're concerned with for graphing purposes, this equation has no solution. And therefore, there are no x-intercepts to this graph. Moving on to y-intercepts, I'll plug in x equals 0 to find those, or that I should say, and I find out that the y-intercept is 5/2, which I'll somewhat arbitrarily place here. Although I can't say it's totally arbitrary because I was careful to place 5/2, which is 2.5, lower than 14/5, which is 2.8. So nobody particularly cares about the scaling of your y coordinates. If anyone really did care about the scaling, then they would just have you graph these functions on a calculator and you'd have perfect scaling. But because we're sketching these without a calculator, we're not going to worry too much about the y coordinates. However, it should be noted that you definitely, in this case, would want to place the y-intercept lower than the whole because 2.5 is lower than 2.8. Okay. Now I found the four features of the rational functions, and it doesn't feel like I necessarily have enough information to know where this graph is going. I know where it hits the y-axis. I know that it has to pass through the hole, with the exception of the hole itself. But beyond that, I don't really have any information. I could plot random points if I wanted to. In other words, you're always free to just pick random x values, plug them in, and find new points on the graph that aren't any of the special features. Nothing wrong with that. I'm going to take a slightly different approach, though. What I often like to ask myself is, how does this graph approach its asymptotes? In what manner does it approach? Where is it while it's approaching? Is it above the green or is it below the green? And as far as the vertical asymptote goes, is it approaching upward, downward, or one of each? One way that you can answer this question, let's start with the vertical asymptote. One way that you can answer this question is to plug in numbers that are near the vertical asymptote. Now remember, this function is undefined when x is -2. That's why there's a vertical asymptote there. But it's not undefined for numbers near -2. So what I did is I picked a number near -2, and I plugged that in. Now, since we're not using a calculator, there's no need for a lot of precision here. But looking at the numerator of this, you can estimate that the numerator would be about 2 squared plus 5, or 9. So call this 9-ish over -0.1. The denominator is so small, or close to 0, that when it divides into this 9-ish number, it's going to be about 90-ish. And so what does that tell me? It tells me when x is -2.1, y is -90. I'm going to put a dot right here to represent that. You can see that it has an x-coordinate of about -2.1. I'm not sure it has a y-coordinate of 90 to scale, but it's close to the end of the graph, and that point really isn't relevant as a literal point. It's more useful in knowing that the graph must be generally going down that direction, and we know that it's going to therefore approach the vertical asymptote in that manner. Still sticking with the vertical asymptote here, having plugged in -2.1 to see how the graph behaves just slightly to the left of that, why don't we plug in a number slightly to the right of -2, such as -1.9. Plugging in -1.9 will give me a similar result, only notice my denominator is positive now. And that means I'm going to get an answer in the ballpark of +90 when I plug in -1.9. I'm going to place that point here and realize that it's vastly far from being to scale. But I'm not particularly worried about that because the only information that I can get from that point that I care about is that the graph must be going upward towards the vertical asymptote in that manner. And you see, by plugging in a number on either side of the vertical asymptote, I at least have the direction in which the graph is approaching that asymptote. And that's very important for me to be able to ultimately sketch this. Now let's turn our attention to the oblique or diagonal asymptote in regards to the end behavior. To know how the graph approaches that diagonal line, we might be well served by finding out if it ever crosses that diagonal line. Well, how do we know if a function crosses the line y equals x minus 2? We set that equation equal to x minus 2. Notice I didn't use the original equation here. It suffices to use the reduced equation because we're looking for a place it might cross, and other than at the hole, these two functions are identical. Now, cross multiplying and subtracting x squared, hit pause if you need to see the algebra slowly, shows us that this absurdity that results indicates that the original equation has no solution. And if the equation has no solution, then those two graphs, and by that I mean the reduced function and the oblique asymptote, must never meet. And so that answers the question that whether or not they meet. The function does not meet its oblique asymptote. There are cases where a function can cross or meet the asymptote, but that doesn't happen here, as you can see. Well, if the graph never touches or crosses the diagonal asymptote, but yet it's approaching the diagonal asymptote, there's really only one other conclusion I can draw, and that the graph must be approaching this way so that it can meet up with the behavior near the vertical asymptote at the bottom, and it must be approaching this way so that it can connect the whole, the y-intercept, and the other asymptotic behavior around negative 1.9. Altogether, therefore, taking all this information into account and connecting it all up leads me to the final graph of this problem. Let's take a look at this example. Going through the 4 steps, let's first analyze what the vertical asymptotes are for this function. Vertical asymptotes occur whenever your denominator is 0 and your numerator isn't. But the denominator can never be 0 here because this equation has no solution. You can see that by just imagining that it's impossible that a number squared plus 1 could equal 0. It's not logical that that could ever happen, because a number squared can't be negative 1, at least not in the real number sense, which is what we care about for graphing purposes. And since the denominator can't be 0, there must not be any vertical asymptotes in this problem. Let's now examine end behavior. Because the end behavior rules state that if the denominator has a higher degree, then the graph approaches 0 on either end, but the denominator doesn't have a higher degree. And whenever that happens, we have to do long division. Here's the result of the long division. Work is not shown. The important fact, however, is that ignoring the remainder term and looking only at the quotient tells me the end behavior of this problem. What does that mean? Well, the line y equals 3 is right here, and that means that on the far ends of the graph, it approaches that horizontal asymptote. Now let's take a look at the holes in the graph, if any. Holes in the graph occur whenever the denominator and the numerator are both 0. But there's nothing that even makes the denominator 0, so there are no candidates for holes in this graph. Therefore, there are no holes either. And for our fourth feature, let's take a look at the intercepts, starting with the X-intercepts. X-intercepts are found by setting our numerator to 0 and solving. The mechanics of solving here are as follows. I divided every term in the equation by 3, factored, and set each factor to 0, and solved. This really isn't the main point of the video. The point is that by setting the numerator to 0, I have 2 solutions, 2 and negative 2, and therefore 2 X-intercepts. As far as y-intercepts go, we can find that by plugging in x equals 0. The math will show that the y-intercept is negative 12, which I'll put right here. This might be a good moment, I'm not done yet, but this might be a good moment to stop and talk about the tick marks on the x-axis and the lack of tick marks on the y-axis. As a general trend, most mathematicians pay much closer attention to the x-axis values here than the y. In fact, we often don't even draw the y-axis to scale or to the same scale as the x-axis. And so when it comes to plotting points like -12, you could certainly put 12 tick marks going downward to show that you have -12 there. But because there's less of an emphasis in general on the y-coordinates and a much more heavy emphasis on how the function behaves for various x values, such is the tradition. And I wouldn't put a lot of time or energy worrying about where you put +3 or -12 on the y-axis, as long as it's roughly reasonable. No one's going to pay much attention to that. Now, what do we know about this graph? It goes through the 3 points that you see there, and it has to approach the horizontal line y equals 3 on the extreme left and right ends. But this raises an interesting question. When the graph approaches y equals 3 as its end behavior, does it approach from above the asymptote, or does it approach from below, or does it do different things on the left than it does on the right? Well, every case is different, but I want to show you how I ruled out approaching from above here. What you see here is not what happens in this graph, but assume for a moment that I hadn't said that and I was simply questioning, does this graph approach the end behavior or the horizontal asymptote from above? Well, the only way that the graph could do that is if it had some kind of shape that looked like this. And that's possible on first glance. And by the way, the graph can cross the horizontal or diagonal asymptote, unlike a vertical asymptote, which can never be crossed. But if a graph is to cross its horizontal asymptote, it would have to meet at some point, wouldn't it? And wouldn't that mean that there was some point on this graph whose y-coordinate is 3? Well, if it is going to cross, which by the way it doesn't in this case, but if it were to cross, then we could find that point by simply setting y equal to 3. That would find the points on the graph whose y-coordinates are 3. Algebraically, solving this by cross-multiplying and subtracting 3x squared from both sides, hit pause if you want to examine the algebra. But the algebra shows that this is an absurdity. 3 equals -12 can never be true, and therefore the equation at the top can never be solved. And therefore there is no point on this graph whose y-coordinate is 3. And if there is no point whose y-coordinate is 3, then the graph must not approach from above, because then it would have to cross. And that logic leads me to conclude, therefore, that in this case, the graph must approach the asymptote from below on both sides. And now that I know 3 points on this graph and the manner in which it approaches its horizontal asymptote, I essentially have a good enough sketch of this graph, and I'm now finished with this problem. One last thing I'd like to add before we conclude the video, especially since I suspect that many people watching this are students in a math class, is that because we're graphing these things without a calculator, there's no reason to be overly concerned about accuracy. For example, one of the problems we saw earlier looked like this. This is actually a 2-scale precise drawing of this function that we saw earlier, and I won't worry about the equation, but it's 2-scale and precise because I used a computer to draw it. But you won't be doing that. If we were using a computer to draw things, we wouldn't be learning all these skills in the first place. And so if you ever come up with a picture like this, for example, and you think, well, that looks, and then you check your answer, which is the supposed correct answer on the top, and you think, well, they look nothing like each other. Remember, we're just looking for a sketch here. Notice, they both have the same asymptotes, vertical. They both have the same horizontal asymptote, or end behavior. They both have the same X-intercept, and they both have the same Y-intercept. As long as your key features match, it doesn't really matter how ugly your graph is. So don't worry about that too much. I want to thank you for watching this very extensive video on graphing rational functions, and that completes the lesson.